this coming Monday, but 1 week from Monday, and it'll be chapter 3 and chapter 4, probably all in chapter 4. In chapter 3, projectile motion, you could see just sort of very simple projectile motion problems, and likely will, but you'll also see some where you have more complicated math, where you have to do more a system of equations. So with those, big thing of reading is just reading the problem and knowing what the various values are. And sometimes, as we've found in problems, they aren't stated. So the homework will help with that. Those extra problems I gave you will help. You can look back at old tests as well to get a feel for what kind of problems will be on the test. All right. So.
Test about chapter 4. Most of the approaches like chapter 3. I checked the old tests. They're not more about chapter 4 than chapter 3.
Well, yeah, figure out. Like on this test, it'll probably be about equal. All right. So probably about equal chapter 3 and 4. Okay. You could also, we had vectors on that test, and you could see just a plain out vector problem. I just give you a couple of vectors and ask you to add them up, like you did in lab. Those of you that are in lab, or like we did in class. Let's say we started on Newton's laws last time, and at the end I showed you that video, that Veritasium video, where he gave his 3 incorrect laws of motion, and they were, the first was that if an object is motion, it'll tend to come to rest. Right, that's incorrect, but that's sort of a view that most people have. The second one is that if you apply a force, you cause an object to travel at constant velocity. And like his example is, you ride in a car, right? You're constantly applying a force, and yet you just travel at, say, 30 miles an hour, right? So with a force, you get a constant velocity. And then the third is that if you have 2 objects contacting one another, the bigger object will exert a larger force than the smaller object. Remember, you had the big rock and the little rock, and the big rock exerted a big force, and the little rock exerted a small force. But all 3 of those are wrong, but those are generally the misconceptions that people have about motion and about forces. And they've been sort of long held for, thousands of years. So it takes a lot of mental gymnastics to get rid of those. Now, Newton's first law says that an object moves with constant velocity. Unless acted upon by a force. And this constant velocity can be greater than 0, or it can be equal to 0. So basically he's saying that if an object is in a state of motion, then it's going to stay in that state of motion unless a force acts upon it. So if an object is at rest, it's going to stay at rest unless you apply a force to it. If it's in motion, it will stay in motion at that velocity until a force acts upon it. Now, this might seem obvious to you now, but it's not really that obvious, because if you look at things tend to be in what state? If you just look around, what are they? Right, they tend to be in rest. Like we're all sitting here, we're all at rest. Everything basically that we see is at rest. And even if we put something into motion, it will tend to come to rest, right? And that's generally, when Newton came up with this first law, that was generally the idea that was held, was that objects tend to have a natural state, and that is at rest. So objects have a natural state. This is the view that was held to be at rest. And Aristotle, of course, who predated Newton by, hundreds of years, thought that this was the case, that every object had this natural state to be at rest. And it was more than just like, well, in the world things tend to come to rest. It was sort of a metaphysical thing where he said that, if you take something out of rest, like he talked about shooting an arrow into the sky, then it's like you're tearing the fabric of what that object is. That you have to you have this very violent excursion from the restful state. So when Newton came along and expressed this, it wasn't just a physical thing, but it was also sort of a philosophical idea as well, or disrupting this philosophical idea. So Aristotle then believed that objects had a natural state to be at rest, and then Newton said, no, that's not true. Their natural state is whatever state they're in. In fact, objects don't really have a natural state so much, that it's just whatever they're doing at the time, whether it be moving or not moving. Before we move into Newton's second law, we need to define what is a net force, because we're going to be talking about a net force. And we'll write it in a couple of different ways. We can write it as the sum of the forces, or we might also write it as F net. These are vector quantities. And what this means is, this sigma right here, what does it mean? Right, so this is a sum, but it's more than just an arithmetic sum. It's a vector sum. So whenever I talk about the net force, that's going to be the sum of all the forces, the vector sum of all the forces. And remember, with a vector sum, if I have one vector here, one vector here, the sum of those two vectors looks like this. In order to get the sum of those vectors, you have to go through those steps where you find the x and y components of the vectors. You take the sum of the x components and the sum of the y components, and that gives you the x and y component of the new vector, and then you find the magnitude and direction. So all those steps that we did in chapter 3, where we summed up vectors, you'll also need to do here whenever we do a vector sum. We'll do several examples, so don't sweat it right now, but just want to let you know that we're going to see that again. And any time that I talk about a net force, that means a vector sum. Okay, let's try to have a couple of questions here. If an object moves with constant speed, the net force equals 0. Is that statement true, or is that statement false? If an object moves with constant speed, the net force equals 0. All right, so a few more seconds. Stop at 50. We have 16, really? 2, 5, 8. We do, yeah. Stop at 50. Okay, let's see. This is a true statement. If it moves with constant speed, that means there is no external force acting upon it, right? Go back to Newton's first law. An object will go at a constant velocity unless an outside force acts upon it. So if I have a constant speed or a constant velocity, that does mean that the net force equals 0. We'll think about it in terms of Newton's second law, which we'll come to next, and that is that F equals ma, the net force equals ma, and so if this equals 0, then that means that the acceleration is also 0. So constant speed means acceleration equals 0. So our force is equal to 0. So you can think about that in terms of Newton's first or second law, which we'll see in just a second. Okay, so inertia is the tendency of an object to continue in its original state of motion. And mass is simply a measure of inertia. So mass is a measure of how much material is within an object, but it's also a measure of its inertia. So we measure inertia in the same way that we measure mass. So if we were to talk about inertia having units, which we don't usually talk about having units, but if we did, we would talk about it in terms of kilograms. All right, so say for example, anybody golf? No golf? No golfers in the group? Okay, well when you golf, right, you don't golf either, but you hit a golf ball, right, a little golf ball, and it's fairly easy to get it to move. But can you imagine that you were golfing and instead of a golf ball, you used a bowling ball? Would that be easy or difficult to put into motion? It'd be extremely difficult, right? Because it has a lot of inertia. It just requires a lot of, it has a great tendency to stay in its current state, which is at rest. All right, so for example, a bowling ball has a lot more inertia than a golf ball. Because it has more mass. So it has a greater tendency to stay in whatever state it's in. Alright. We'll come back to inertia in just a bit, sort of as a concept, because it's closely related to both Newton's first law, which is called the law of inertia, and Newton's second law. Okay, so Newton's second law says that the acceleration is directly proportional to the force, that is, that A is proportional to F, and also that the acceleration is inversely proportional to the mass. A is equal to 1 over m. So if I were to write this in an equation form, taking these two relationships, I would say that A is equal to F over m, or, as we would usually say, F is equal to ma. Now this is the net force that I'm talking about here, so we would write it in that way. Sometimes I'll leave the net off just because I'm kind of lazy like that. But also you could write it like this, that the sum of the forces equals ma. Alright? We're going to get into momentum later, and we'll talk a little bit about this, but just sort of as an aside here, let me show you in case you're interested. Because Newton didn't really write Newton's second law like this. He wrote it more in terms of momentum. Now momentum is equal to the product of the mass and the velocity. You don't need to write this down right now. We'll get to it in chapter 5 or 6. But momentum is equal to mass times velocity. And so what Newton said is that our force is equal to our change in momentum over our change in time. But you can see that this is the same, because if I have dp dt, that is dmv dt, if our mass is constant, as it usually is, this is equal to m dv dt. And dv dt is what? That's our acceleration, right? So that's our acceleration, m times a. So we'll see that how that's sort of interrelated in terms of momentum, but Newton actually wrote Newton's second law in terms of momentum, not as this F equals ma. All right, but we'll deal with it in these terms. Now, more specifically, we can extend our Newton's second law to 3 dimensions. Sorry. And we'll do that. That is to say that the sum of the forces in the x direction equals max. The sum of the forces in the y direction equals may. And then also the sum of the forces in the z direction equals maz. So anytime we come upon a problem, we're going to split everything up. We'll have our forces in our x direction, our forces in our y direction, and if we have forces in the z direction, we'll split them all up, and then we can apply Newton's second law in terms of the individual axes. Okay, so in doing so, we'll be able to set up a system of equations, and just like we did in chapter 3, solving that system of equations. Usually we won't deal in the third axis. All right, I want to show you a little video, and then we'll come back and we'll work this little problem. An inertia. And so when we're talking about things moving or requiring forces to move things, it's the inertia that we're really concerned about. Now, if we're lifting things, then it's the weight, right? So I like to tell people who cycle, because I like to cycle. Anybody else like to cycle? Like Hunter, I know your brother does, right? And they pay an obscene amount of money for these really light bikes, right? Like you can pay tens of thousands of dollars for a really light bike, or at least several thousand. But you know, around here, it doesn't really matter that much to have a light bike. And why is that? Because it's flat, right? So, I mean, you can have a really heavy bike and still go fast. It's just, initially you'll need a big force to get up to your constant velocity. But then after that, unless you come to a hill, it doesn't really matter if your bike weighs, 3 pounds or if it weighs 50 pounds. now with expensive bikes, there are other things that make them fast other than just the weight. So I'm not saying they're not worth it, but well, maybe I'm saying that. But anyway, I guess your whole family, right, Hunter? Cycles?
Yeah, everybody but me.
Everybody but you. Yeah. Let's see. So let's work NCAT problem. Oh shoot, where is it? Okay, I remember what it was. It was I forgot to bring it. I'm sorry, but it was, say that you have a rocket ship, has a mass of 1,000 kilograms. Right. Your thrust, or the thrust on the ship, is, say, 20,000 newtons, 20 kilonewtons. What is the velocity of the ship? After 8 seconds. Or let's make it 10 seconds. But what is the velocity of the ship after 10 seconds? I'll give you a few minutes. Because see some kinematics stuff on this next test. The kinematics is never really going to go away. In this case, it's a kinematics problem, but I want to know what is the final velocity of the rocket ship. All right, does anybody have the answer? Yeah. What is it? 200? All right, so let's see. First, we want to find the acceleration. My acceleration is just F over m. Right, so my force is 20,000 newtons over my mass, which is 1,000. So let's write 200. So let's see, this cancels, leaves me with 20 meters per second squared. So that's my acceleration. And then if I want to know the final velocity, it's going to be v naught plus at. We'll assume that v naught is 0. So that's going to be 20 meters per second squared times 10 seconds, which is 200 meters per second. All right, so you could see some kinematics in your next exam. Your problems won't be this simple. I'll show you some examples of what they'll be like. But you could have sort of a kinematics thing sort of thrown in there at the end. All right, let's do some quick clicker questions. Can I go down from here? All right, let's say I have this elevator. It's accelerating downward at 2 meters per second squared, and I want to know what is the tension in the rope. Now in these problems, your first step, you'll go through several steps. First, you'll identify and label the forces. So how many forces are acting on the block in this elevator? There are 2 forces acting upon it, so you'll need to identify those forces and label them. The second, you'll need to draw a coordinate system. Draw and select a coordinate system. All right, in this case it's pretty simple because the forces are all along which axis? The y-axis, right? So we have the tension and the weight. And then third, you'll want to resolve the vectors into their x and y components. And then 4, we'll apply Newton's second law. That is, it will say the sum of the forces in the x direction equals max, and the sum of the forces in the y direction equals may. And you'll use these steps on every problem that you do for this chapter. Identify and label the forces, draw a coordinate system, resolve the vectors in their x and y components, and then apply Newton's second law and solving the equations that result from that. Now this one's pretty straightforward, but try it. First, identifying and labeling the forces, the tension, and the weight. Draw your coordinate system. Here you only have one axis, so it's fairly simple. I mean, all the forces are only on the y-axis. And because of that, you can skip that part 3, and then apply Newton's second law. Alright, maybe 20 more seconds. Alright, I'm going to stop at 3:30. 3:30. Just guess if you don't know. Alright. Oh, that's okay. Alright, so let's see. Most of you put B. Were you just doing mass times acceleration to get B? The 8 of you that put B? Yeah, B's not the right answer. Let me show you. The right answer is actually C. So first we want to just identify and label the forces. I have 2 forces, the weight, and then what's the other force? The what? The tension, right. That's what I want to know, is what is the tension? Let's see, I'll call it FT. What is FT? So that's the first step. I've identified and labeled the forces. Now I want to draw a coordinate system. I'm going to use this coordinate system. It's sort of a moot point because all my vectors are on the y-axis. So I can really just skip right ahead to step 4, where I apply Newton's second law. So Newton's second law says that the sum of the forces in the x direction equals max. The acceleration in the x direction is 0. In fact, the sum of the forces, there are no forces, so I don't even need to write that. So really, I just jump straight to this. I say the sum of the forces in the y direction equals may. Alright? Now, the sum of the forces in the y direction, if I were to write the sum of ft and fw, how would I write the vector sum of those 2 forces? Michaela? How would I write the vector sum of ft and fw? Ft, is it positive or negative? It's positive, and fw is positive or negative? Right, so I just write it in that way, plus ft minus fw. Very good. So ft minus fw, that's my vector sum of those forces, is equal to the mass. Okay, and here, what is the acceleration? Nobody put A, actually. That's good. What is the acceleration? No, it's not negative 9.8. 2 meters per second squared. But what is the direction of the acceleration? is down, so my acceleration then is -2, right? So acceleration in the y direction, this is equal to -2 meters per second squared. All right, now I want to solve for Ft, and that's going to be Fw plus MAY. All right, now Courtney, that 9.8, or 10 meters per second squared, that comes into play for the weight, right? But we have an additional acceleration just due to the elevator's accelerating. So here I get my mass, which is 10 kilograms, times 10 meters per second squared, plus 10 kilograms times -2 meters per second squared. So that's 100 minus 20, which is equal to 80 newtons. So my tension in the rope is 80 newtons. Notice, excuse me, notice that if it wasn't moving at all, then, like if it wasn't accelerating, what would the tension in the rope be? It would be 100 newtons, which is equal to the weight. Right, but because it's accelerating downward, then the tension in the rope is going to be equal to something less than 100, but not 0. What if this object was accelerating in free fall? That is, the acceleration downward was -10. What would be the tension in the rope? It would be what? 0, right? So if it were in free fall, there would be no tension in the rope at all. Right? That's what we call weightlessness. When you have something that's falling, like if you're in space and you're continuously falling to the surface of the Earth, which is what you do in space, you orbit around the Earth, or you continuously fall towards the surface of the Earth, that's free fall. And if you were attached to a rope, you would have no tension in the rope. All right, let's try this one. This one's a little more complicated, not terribly more so. First, you want to identify the forces. In this case, there are 3 forces. Then you want to draw a coordinate system. You'll just draw a normal XY coordinate system, not rotated or anything. Then you'll resolve your vectors into their X and Y components. And then you will write out Newton's second law, apply Newton's second law. And I want to know what is the tension in the rope on the right. I'm going to start filling in a few things here. So I've taken you up to step 3 on the board here. You'll need to resolve the vectors and apply Newton's second law. In this case, what is the acceleration of the block? What is it? It's not a trick question, is it? It's not moving, no. The acceleration due to gravity is -10, but this object is not moving at all, right? So this is 0, right? Step 3 is find the x and y components. Now we're done here. It's another minute or so. That should be an L. Oh, no, sorry, that should be cosine. I'm going to stop at 6:50 or 7 minutes. I'll give you another 10 seconds. Just guess if you don't know, though. So 7:10, I'm going to stop. 7:10. And this is more like what you'll have on the exam, but again, on the exam, we'll work through problems later in the week, but your exam will be similar to this, but more complicated. You'll have more bodies to deal with, but you'll still follow the same procedure. You're always going to follow the same procedure. There's 4 steps. Label and identify the forces, resolve or find a coordinate system that works, resolve them into their x and y components, and then apply Newton's second law. Let's see, the answer here was A. Majority of you won. So once I get to this point, I say the sum of the forces in the x direction equals FTR cosine of 50 minus FTL cosine of 50, and that's equal to MAX. Now AX is equal to what? We already said this, but what is the acceleration? Is 0. This is called a statics problem. Those of you in engineering, you'll have to have a whole semester of just this, basically, and you'll go into much greater depth. And actually, later in the semester, we'll do elasticity and equilibrium, and we'll spend a lot more time on statics and finding solutions to static situations. So this is a statics problem. That means that the acceleration equals 0. Now that means in this case it's not moving at all, but that can also mean the acceleration is 0, meaning that it's moving at a constant velocity. But in this case it's not moving at all. So from that, we can say that FTR is equal to FTL. That the result of this equation is that the two force tensions are the same. Okay, so I'm just going to say, instead of differentiating between left and right, I'm just going to call that FT. So I don't think I said that, but L and R were left and right, like the left rope and the right rope. Okay? You could probably just look at that, and because it's symmetrical, you might just be able to intuit that those tensions are the same, perhaps. But if not, it fleshes out when we apply Newton's second law. Now, when we do the sum of the forces in the y, now that we know that these forces are equal, I can just say 2ft sine of 50 minus Fw equals 0. And since I'm looking for the tension, now I just solve for this. So it's Ft equals Fw divided by 2 sine 50. That is equal to 23 kilograms times 10. That's the acceleration due to gravity, but notice that I use a positive value. 2 sine 50. That's equal to 150 newtons. Let's see. Some of you did put B. Probably when you put B, you didn't include this factor of 2. That you solve for the tension, but you didn't include the 2. But we very clearly have 2 tensions up here. All right? 150 newtons. Don't worry, we're going to work through more problems, but your problems will be two-dimensional. That means that you'll have some forces that are on axis and some forces that are not on axis. And likely your problem for the exam will also include 2 bodies, 2 or more bodies. They're simple. You still follow the same procedure. You just get more equations in the end, so it's just a little more difficult to work with. Okay? You need to be able to master these problems first, though. So if you're having trouble with this, there are some homework problems that are sort of this difficulty. Take a look at those and make sure you're on board with them, okay? All right, let's see. I've already been using the units of force, but let's just sort of take a quick segue. The SI unit for force is the Newton. Okay, just a quick little grammar thing. Have I told you about abbreviations of units? Have I told you this? So for grammar purposes, and I don't care, but in case you're interested in grammar, whenever you have a unit that's named after a person, whenever you abbreviate it, you capitalize it. So like in physics, a lot of units are named after people. The Newton, I don't know, the watt, the joule. There are a lot of units named after people. And whenever you write them out as a word, you don't capitalize, but when you write them out as an abbreviation, you do capitalize. That's just a little trivia for you. All right. In U.S., what's the unit for the force? In the United States, what do we use for force? Right. So we use pounds, which is lb for reason. Anybody know why lb is the abbreviation for pound? Do you know? Nobody else knows, so you could just make up something if you want.
One feels like a Latin word.
Is it Latin? Okay. All right, so, for example, I weigh about how many newtons, you think? Don't say 1,000. No, I weigh about 700 newtons. So a typical person weighs about 700 newtons. A small apple is about 1 newton. And then also, I think we might have already said this, but do y'all know what the British unit for mass is? Remember, there's a difference between mass and weight, right? So in the metric system, we use the kilogram for mass and the newton for weight. So in the British system, we use watt for mass, and then we use pound for weight. What do we use for mass in the British system? I think I might have told you. It's the slug. Did I tell you all this, or did you know that? Isn't that cool? It's the slug. That's the British unit for mass. You're not going to be tested on that. It's just something to tell your friends and like make them think that you're cooler than you actually are. Not that y'all aren't cool, but I mean, sitting with a bunch of engineers and chemistry majors, for goodness sake. So, all right. Geomatics too. Sorry, geomatics. which are probably going to be the highest paid people when we graduate, unfortunately. Chemists, y'all make good, but engineers too, I guess. Oh my gosh, y'all are all going to make a lot of money. Make more money than me. Okay, so it is possible to have motion without a force. Is that statement true or false? It is possible to have motion without a force. All right, I'll stop at 50. I think that's everywhere. 258, 68. Yeah, I'll stop here. Possible to have motion. Now that's a true statement, right? So, if I have something, or maybe that was a little confusing, but if I have something that's moving, it can be moving without having any forces acting upon it. Now, at some point in the past, there had to have been a force that acted upon it. Is that what y'all were thinking? If you put false, okay. Let's see. I'm not going to mark either one correct then. I'll just leave them both open. So it is possible to have motion without a force. That is a true statement because you can have something moving and not have any forces acting upon it. Okay. So the answer there is true. If an object isn't moving, no force acts upon it. That is, if an object is stationary, no force acts upon it. Is that statement true or false? Is it necessarily true or false? All right, so a few more seconds. Okay, B is right. Very good. All right, so if an object is stationary, no force acts upon it, that's false. All right, prime example, all of us right now, right? We're all sitting and we're stationary, but there are a whole host of forces that are acting upon us. First, there's the weight of us, there's the force due to gravity, and then the chairs are pushing back on our butts, holding us up, right? There are other forces like intermolecular forces within our bodies, there's electrical forces, there's all sorts of forces that are acting. So this answer, if an object is stationary, no, is false. All right, let's fill in this for Newton's third law. We'll come back to this on Monday, and then we'll wrap it up. So if objects 1 and 2 interact, then the force F12 exerted by object 1 on object 2 is equal in magnitude but opposite in direction. So when we go back to that, we have the small rock, remember the incorrect laws of motion, and the big rock, and they were pushing on one another. If this rock is exerting a force in this direction, this rock is exerting an equal force but opposite direction, equal magnitude but opposite direction on this smaller rock. All right, we'll get into Newton's universal law of gravitation a little bit later in the semester, and we'll deal with that in more detail. But Newton's third law says that if you have one force, you have another force that is equal but opposite in direction. I think that's all of our time for today. But on Monday, we're going to work through some more problems that'll be more like what you'll have on your test in about a week and a weekend. All right, y'all have a great weekend. Be safe.